Hey everybody, it's Friday, December 18th, and as you can see here in the aim today, our goal for this video is to describe the motion of a conical pendulum. So the first obvious question that we can ask here is, what on earth is a conical pendulum? You've actually probably seen these before, whether you realize it or not, because they look like this. This amusement park swing ride, if you've ever even seen one or been on one, is an example of a conical pendulum. And so the way it works is not that complicated. When you go to an amusement park and you see this ride before it started, it looks something like this. All of these swings are hanging from those ropes and they're hanging straight down. And once the machine gets revving and this top part here starts spinning, then the swings eventually fly out and sort of look like this. Really, of course, on the swing ride, they look like this. And so before we actually get into like the real diagram for it, let's just go ahead and watch it for a moment. And so the actual motion of this thing is going to look something like this. And so you can see here, this thing is going to be spinning. If you had a ball attached to a string, you can like do this at home, really. I always used to do it in class with a computer mouse, if you have a computer mouse that has a wire on the end of it. If you take it and you let it hang straight down, obviously the string is just going to sit there. It's going to be, just hanging down. But when you start to spin it, you'll notice that as you spin it faster and faster and faster, it's going to swing out at an angle like this. And so, of course, it may seem kind of weird because this thing is moving at an angle that we're talking about this when we're talking about uniform circular motion. But I think it's pretty clear if you look at it from the side view, and that's what I like this simulator for, you can see that for the conical pendulums we're going to be talking about for this class, we are always going to be dealing with these situations where the object is swinging in a purely horizontal plane like this. And that if we look at it from the top view, it's really important to realize that this thing is just moving around in a circle like any other object moving around in a circle. The difference, of course, is what happens when we really take the chance to consider the forces that are acting on it. Because it's being swung around in this particular way, an accounting of the forces is going to reveal to us some interesting relationships. What I think is important to recognize, though, as we are going through this, is that already you can observe something if you play around with it, if you have something at home that is attached to a string. Or literally like if you just have string and you tie something to it. When you swing it really, really slow, you notice that it makes this kind of small circle, and the angle it swings out at is not particularly large. But when you swing it faster and faster and faster, you notice that the angle that this thing makes with the pole, the angle that the string makes with the pole, gets bigger and bigger and bigger, and that plane that the ball is swinging in rises and rises and rises. So notice when the angle is small, the plane is all the way down there and it's small. And as you increase the velocity here, notice the radius of that circle gets bigger. We can tell that for sure. When we look at the top, the radius of that circle gets bigger when it gets faster. And of course, we can also see when we look from the side view that the angle is going to change. And the point that I'm trying to make here is that the analysis that we are going to do is going to reveal all of those relationships. And so I'm actually going to go ahead and leave that open for now as we go through the rest of the material here today, and then we'll come back to that. So the first question here is, well, why, when the thing is in motion, does it swing out at an angle like that? Clearly, we can see here that this thing is attached to a rope. And so I hope it's pretty clear as to what's going on there. But the fact that the thing is swinging out at an angle here is a little bizarre. But I think it's important to realize here, if you really think about it, it makes good sense. The reason why these chairs, especially on the swing ride, swing out like that is because the people in the chairs, and really the chairs themselves, have inertia. And so if we see this thing actually in motion, you can see here that it's the inertia of the people which want to carry them in a straight line that makes the chair swing out. And of course, we actually know that this is true, that the people have a tangential velocity because, well, that's just how circular motion works. And unfortunately for this person on this ride, they had to figure that out the hard way as this thing swung around. They have a little bit of a tangential velocity. Now, lucky for that person, they were just fine after that incident, so no harm, no foul, but a little bit of physics there. And so essentially what we're going to have here in this simplified version is the motion of a conical pendulum looking like this. I'd actually like you to sketch this in your notes. This is a super important diagram. So I'd like you to take this. I'd like you to sketch it in your notes. And what I want to do here first, because we've been talking about forces for like a heck of a long time by now, and I think you guys do really know enough to be able to figure out what's going on. And of course, because this is a forces problem, we are talking about circular motion. And whenever we talk about circular motion, we're always talking about forces. The way that we are going to analyze this situation is by using, you guessed it, a free body diagram. Now, when we draw the free body diagrams for these problems, and we really never do this otherwise, but when we draw the free body diagrams for these problems, we're going to put the dot like we always do. That's not the part we never do. But we're also going to add a dotted line here showing the rope, just to make it very clear that this is the situation that's happening. And so what I'd like you to do, because I really do believe that you can do this on your own, is I want you to visualize, because we saw in that simulator, the motion of this conical pendulum. And I want you to think, what forces are acting on the object? And I want you to take a second to try to sketch the free body diagram. And when you hit play, we'll go over it. So it should be clear to everybody, I really don't think this is going to be a mystery, that we're going to have a force of gravity acting downward on this object. Of course, that's always true whenever the object is located on the Earth. And yeah, of course, this object is located on the Earth. And so that much should be obvious. Also, this object is not only interacting with the Earth, it is also interacting with the string. And so there is a force of tension exerted on the object here, and it acts in a direction along the string, like this. And so I'm sort of exaggerating this arrow here because now I've just drawn it horribly, but we're going to just label this here Ft. And so we have two forces here. We have a force of tension acting at an angle, and we have the force of gravity acting straight down. And those are the only two forces that are acting on this object. And so to give it a little bit of a better look here, I think, we could take a look at this diagram. This diagram here, I particularly like because not only does it show the force of gravity acting down and the force of tension acting up at an angle here, but it also lays out a super important truth about a conical pendulum, which is that the interior of the cone here is a right triangle. And this is really important. And I'm actually going to write here, note, the cone's interior is a right triangle. That's going to come up for sure. So you should be prepared for that. And like I said, this is just like a super, super, super important diagram. So I'd like you to take a minute here to pause this video and go ahead and sketch this diagram, labeling the individual parts of the triangle, L here, because this is the rope's length, H, the height of the cone, and R, of course, here is the radius of the circular path, as well as the two forces. And then we'll move on and go ahead and do an analysis. And what I really like about this diagram in particular is that not only does it give us a labeling of the parts of the right triangle and the two forces that are acting on the object, but it also brings to mind a really, really important question that we have to ask and answer. If we have this object moving around in a circular path at a constant speed, how is that possible? look at the two forces. In order for a force to cause an object to move in a circular path, the force has to act toward the center of the circle. What force is acting towards the center of the circle here? In other words, what force is responsible for providing the centripetal force? It's not gravity. It's the x component of the tension that acts toward the center of the circle. And so what we're going to say here, these are two extremely important notes for you to write down. The function of the x component of the tension, or of the horizontal component of the tension, is to provide the centripetal force acting on the object. It's acting towards the center of the circle. On the other hand, that leaves us with a really super important question here. And I'm actually going to go back to the diagram for a second. So if you're writing this down, just hang on a second. I am going to come back to this. This leaves us with a really important question, though. If there is an x component of the tension, which is acting towards the center of the circle, which is providing the centripetal force, then what is the y component of the tension doing? What is it doing? Well, look at the diagram. If the function of the x component of the tension is to provide the centripetal force acting on the object, then the function of the y component of the tension is to cancel out the weight of the object. And that's the deal. Take a second to pause this video here and write that down. And when you hit play, we'll take a look at the equations. Okay, so taking a look at the equations, it's important to realize here, once again, as with many other problems that we've had so far this year, I'm going to split this slide in half. And that's because we're going to have an equation for the x direction, and we're going to have an equation for the y direction. Let's start with the y direction just because it's about as easy as it can get. We said here that the y component of the force, Fty, we'll label it, is equal to the weight of this object, or the force of gravity. And so there's not a whole lot that we can do with this equation, because we know that the right-hand side of this equation is just going to be mg. And so the question that we have to ask here is, well, what is going on with the left-hand side of this equation, with Fty? And this is one of those problems where you have to be careful. I'm going to go back to the diagram for a second. If we go back to the diagram, and you'll notice here, the angle given in these problems is always the angle from the vertical. And so because here we're dealing with the angle from the vertical, the y side of this triangle is not the opposite side like it usually is. It's the adjacent side of the triangle. And so that means the y component is going to be related to the cosine of the angle. And so we're going to write here, Fty is Ft cosine theta. And that's really all that you can do with this side of the equation. And now because I have room over here, I'm just going to write, note, since theta is the vertical angle between the rope and the string, between the rope and, well, and the vertical axis, sine e cosix, that saying that sine goes with y and cosine goes with x, reverses like an inclined plane. So about a month ago, I lied to you. Because when we were covering the inclined plane, I said you have to remember sine and cosine switch for the inclined plane, but fear not, that is the only problem for which that is true. That's just because I wanted you to remember that then. But now, I am telling you the complete unvarnished truth when I tell you the conical pendulum and the inclined plane are the only problems in this course where you will have a vertical angle. It's a fact. And because it's the vertical angle, the sine and cosine switch. Sine, instead of going with y, goes with x. Cosine, instead of going with x, goes with y. Moving on to the x direction here, as we said, the purpose of the x component is to provide the centripetal force. And so we're going to say here that ftx equals fc. And so that means ft sine theta, sine goes with x now for this problem, is going to be equal to mv squared over r. And depending on whatever we have with this problem here, that's what we're going to be applying to go ahead and try to solve this problem. This is really important. Take a second to pause this video here and write that down. And when you hit play, we'll move on. So in summary, the situation looks like this. The y component of the force of tension is given by the equation ft cosine theta. That balances out the force of gravity. Remember, when I showed you from the side view earlier, and I'll come back to that now, I suppose. When I showed you from the side view earlier, this thing is moving in a purely horizontal plane. And because it's moving in a purely horizontal plane, it's not accelerating up or down, this way or this way. And so the idea is, because it's not accelerating up or down, the y component of the tension has to cancel out the weight. And additionally, because the thing is moving in a circle, we can see here, whether you want to look at it from the top or from the angle, that the x component of the tension is an unbalanced force. It's the net force. And because that force happens to be pointing toward the center of the circle, always, it's providing the centripetal force acting on the object. Pretty cool. And so the situation looks like this. And what I think is important to realize is that sometimes conical pendulum problems don't look like conical pendulum problems. For example, this is a conical pendulum problem. This problem here says, what angle does a plumb bob line make with the vertical in a train rounding a 280 meter radius curve at 35 meters per second? If you have just like a pair of headphones, because that's probably going to be heavy enough to do the trick. It's a wired pair of headphones. And you round a corner holding those pair of headphones, you realize that as you round the corner, your headphones want to continue moving in a straight line. And so they do continue moving in a straight line. But you, by pulling on the cord of the headphones, actually pull them away. And so effectively, you get a miniature version of a conical pendulum. The thing is not actually moving in a circle. The whole train upon which this object is on is moving in a circle in this problem, but that's the basic idea. This problem's a little confusing to understand because it says a plumb bob line, but if you don't know what that is, a plumb bob line is basically just a heavy object attached to the end of a string that basically just determines the vertical. It hangs straight down always because of the force of gravity, so it's essentially something to have a reference for what is straight down. And so essentially, this big heavy thing, when which is attached to the string, when the train is not accelerating from side to side, just hangs down straight vertically. But when the train turns, the object swings out a little bit because it wants to continue going in a straight line, but it's attached to the ceiling of the train, which is now rounding a turn. Like I said, I think this is kind of complicated for you to understand if you don't actually see it. So take anything, even if you take like your phone charger and you unplug it from like the power brick at the end and you just hold your phone dangling from the end of it. If you just walk forward with your phone, you'll see that your phone is hanging straight down. And if you turn a corner or just start walking in a circle, you'll see that your phone will actually swing out, sort of like how the conical pendulum looks like it's swung out in all of those diagrams. The reason why is because your phone's inertia wants to keep it going in a straight line, but you walking around in a circle makes it swing out at that angle. And that's the deal here. So let's go ahead and solve this problem. The first thing you want to do when you're going and solving this problem is to make your list of knowns. So let me actually pop back to that slide for a second. It says here we've got this train rounding a 280 meter radius curve. So R is equal to 280 meters at 35 meters per second. Of course, we know here that G is 9.8 meters per second squared. And this particular question is asking us for the angle theta. So what's this going to look like? Well, obviously, or I hope it's obvious at this point, our first move, whenever we are solving a problem such as this, is to draw our free body diagram. And so we're going to draw our free body diagram. I'll go ahead and just label that FBD over here. And our free body diagram is nothing new. We've already sort of discussed what that's going to look like in this video, so I'm going to zip through that super fast. We're going to have our tension here acting in the direction of the rope, and we're going to have our weight coming straight down. It should be clear to everybody by now that we've discussed what we need to discuss. The line for the tension should be longer than the line for the force of gravity. And that's because only the y component has got to be equal to the force of gravity. And so the Pythagorean sum of the y component and the x component has got to be bigger than the weight. Now, as I've mentioned sometimes also, but not particularly in this video, sometimes I think, it's helpful to take a quick peek at a component diagram because it just gives you a sense of what's what. Now, we've already sort of discussed this, but the component diagram is going to look like this. We've got our full vector weight coming straight down. We've got our FTY, which I'm showing as a dotted line here because it's not a full force, it's a component, coming up. And notice these are balanced. And then we have our FTX acting towards the center of the circle, which is producing circular motion. And so we're going to start with our x direction equation. And we're just going to write out the equations. And so what I'm going to write here is similar to what we wrote before. We start with just making basic relationships. So we have FTX is providing the centripetal force here, and I've got FT sine theta, because remember, sine goes with x now, is going to be equal to mv squared over r. Cool. That's my x direction equation. To figure out exactly what I'm going to do with that, it's probably helpful to look at the y direction equation and make a judgment. And the judgment here is pretty straightforward. We have FTY equal to the weight, Fg. And so I'm going to have Ft cosine theta is equal to mg. And now you're taking a look at both of those equations. And what you have to realize, we've got to combine these equations. It's a system of equations that we have to solve simultaneously. And to some degree, once again, I've bamboozled you. Because what I have told you quite a bit is in problems where there's a tension, generally a good strategy is to add them. It's not really going to work for this one because there's no addition at all. So one is not positive and one is negative. That really only works for like Atwood's machine style problems with a pulley. Here, you don't really have much of a choice. Both of the equations have a tension. And they didn't tell us what that was. And they didn't ask me for it. And if they don't tell me what the tension is and they didn't ask me for it, then let's just get rid of it. And we can get rid of it by solving each equation for tension and just setting them equal to each other. And so I'm going to write over here, Ft, according to this equation from the x direction, is mv squared over r sine theta. I'm going to put that in a box because that's just the truth. And then here, in the y direction, I'm just going to have ft equals mg over cosine theta. And that's the truth, so I'm just going to go ahead and put that in the box. And I'm going to write here, and you don't have to like write this every time, but I'm just going to write it here because this is the first example we're doing. I'm going to say to eliminate ft, set them equal to each other. I don't know what it is, and I don't want to know. So let me just get it out of there. And so this line is going to look a little silly. This part I do want you to write. This is literally the only part I don't want you to write here, the sentence. ft equals ft. Yeah, no duh. And so we have mv squared over r is equal, mv squared over r sine theta. Get so used to saying mv squared over r, sometimes you forget the sine theta. Mv squared over r sine theta is going to be equal to mg over cosine theta. The first thing that you should realize, which maybe some of you were worried or confused about, is, well, wait a second, they didn't tell us the mass either. What am I supposed to do? They don't need to tell you because it cancels. The mass of the object does not matter. And that's pretty cool. Because it should be noted, a heavier object would have more inertia. So it's going to need more centripetal force to hold it into the circle if it's heavier. But since the centripetal force is being supplied by tension, which has something to do with the weight, I hope it's clear to everybody that if you hang something very light from a string and something very heavy from a string, the tension is going to be different. And so because the tension is also influenced by the mass, you get that cancellation effect. A heavier weight or a heavier mass, a larger mass, a heavier object needs a bigger centripetal force, but the tension also provides a bigger centripetal force when there's a bigger weight, and so it works out. And so what we end up with here then is v squared over r sine theta equals g over cosine theta. And obviously, I've run out of room. And so I'm going to continue this on the next slide. You do not need to rewrite this step. I'm just going to rewrite it on the next slide. So I've got v squared over r sine theta equals g over cosine theta. And now we have a very interesting issue. Our very interesting issue is that we have to solve for the angle. And that seems pretty hard because we have two terms where there's an angle. So if we solve this for sine theta, like we could take the inverse sine, but the cosine is going to be in the equation. It's not going to work. We could similarly solve it for cosine theta and take the inverse cosine, solve for the angle, but that's not going to work because then it's going to have a sine theta in that equation. But you notice, if you just switch the place of sine theta and g, on one side of the equation, you're going to get sine theta over cosine theta. And on the other side of the equation, you're going to get v squared over rg. Sine theta over cosine theta. It's tangent. And honestly, if you don't think that's cool, then I just feel sorry for you. Come on. All of that work leads us down to a sine theta over cosine theta. If you weren't sitting in your math classes when your math teacher first told you that sine theta over cosine theta was tangent, you have to know that for a test. And you were sitting there thinking, well, that's another useless piece of information that I have to remember. Then look at us. Here we are. It's coming back. It's actually important stuff. It just takes physics to realize that. And so notice here we've got a tan theta equals v squared over rg. This thing's super easy to solve now. To solve for the angle, all I have to do is just take the inverse tangent of both sides. So I have the angle is equal to the inverse tangent of v squared over rg. And I don't want to run out of room here, so I'm just going to do this next to it over here. I've got the inverse tangent of v squared, which is 35 meters per second, whole thing squared, so I'm putting it in parentheses. And then I've got that all over r times g. R, remember, was 280 meters. And g is 9.8 meters per second squared. And when you do that math, 280 times 9.81, and you take your 35 squared and you divide them, you get inside of the expression here, inside of the argument, 0.446429, blah, blah, blah. And if you take the inverse tangent of that, then that's going to give you, to the nearest degree, 24 degrees. And that's it. Let's summarize. For basically every conical pendulum problem, your move is to draw the free body diagrams. Then you write your equations from the free body diagram. 99.9% of the time, they're not going to tell you the tension. Sometimes they ask you for it. Other times they don't. But usually, because they don't ask you for the tension, you set them equal to each other and get rid of it. Even if they do ask you for the tension, you probably need something else anyway first. And so you set the tensions equal to each other, and then you just manipulate the equation to solve for what you need to solve for. But it should be noted by everybody that it's such a clutch tip to realize that if you have a sine and a cosine floating around in an equation, try to get them on the same side of the equation. Because a lot of times it just so happens to work out that the sine's going to end up in the numerator and the cosine's going to end up in the denominator. And that, my friends, is a tangent function. And then that makes this thing easy to solve. So just very quickly before we move on, and I really only want to spend the rest of this video talking about one more problem. It's really the only other thing we have to cover. I said I was going to revisit something, and so I just want to go back to that thing. If you remember, and I'll just show this here, if you remember, we were looking before at this simulator. And what I said here is that when you increase the velocity, notice here that the angle increases and the radius increases. Remember, we can see that when we look at the top view, that the radius increases when the speed gets bigger. So notice I just lowered it again. It's at 3.5. Now, if I raise it up, that radius gets bigger. And if I look at the angle view, as I increase that speed, notice that that angle gets much bigger. Of course, if I eventually increase the speed so much, it's going to get really, really, really close to being at 90 degrees, but it's not quite there. But it gets pretty close. And then as you lower the speed, you can see here clearly the angle is getting smaller and smaller and smaller until eventually it gets really tiny. And so the question here that we want to answer is, well, how exactly do these equations show that? And I think it's most obvious looking at this line. So on this line, we have tan theta equals v squared over rg. And so if we solve that for v squared, we could just solve it for v squared, that's fine. Then we get rg tan theta. And so what that tells you is that v squared is directly proportional to r, and it's directly proportional to the tangent of the angle. And if you just play with your calculator here for a quick second, then you'll see that the tangent of 20 degrees, then you take the tangent of 30 degrees, the tangent of 45 degrees, the tangent of 60 degrees. The number gets larger and larger and larger. The tangent of 20 is 0.36. The tangent of 30 is 0.58. Tangent of 45 is 1. Tangent of 60 is 1.73. So as the angle gets bigger, the tangent is going to get bigger. And this equation shows that when the speed gets bigger, the tangent of the angle gets bigger, which tells you the angle is getting bigger, which is what we see when we look at the simulator. Additionally, of course, when the speed increases, we also see that the radius increases, which is exactly what we saw when we looked at the simulator as well. That's the point. And so with that, let's just go ahead and move on to the last problem. Now, this last problem, I want to be totally clear about, is absolutely brutal. It's more complicated than anything you could reasonably expect to see, I think. Having said that, it is an important problem that I want to look at because it'll sort of be used as a vehicle to teach a lot of these important things that we have to say about the motion of the conical pendulum. All right, so let's take a look at this problem here. It says a 0.750 kilogram ball is suspended on a 0.600 meter cord from a fixed point. The ball swings in a horizontal circular path at 645, no, that doesn't say 645, geez, sorry, at 0.645 revolutions per second. The question says to determine the tension in the cord and the angle between the cord and the vertical axis. So it should be pretty clear to everybody that we've got to deal with this. 0.645 revolutions per second. This 0.645 revolutions per second is actually the frequency. It tells you the revolutions per second. And you may remember this from honors physics. If you do, that's cool. If not, it really doesn't matter. Frequency and period are actually inverses. Remember, we said so far, like just pretty recently, period is a measurement of seconds per cycle, or in the case of an object moving around in a circle, seconds per revolution. This is a measurement of revolutions per second. So what we have is revolutions per second, and what we want is seconds per revolution. And since revolution is not even really a real unit, that's just going to be seconds. And so I hope the point here is clear. If we have revolutions per second, and what we want is seconds per revolution, what we have to do is flip it. And so all we have to do here is take the inverse. And so the period here, which I never want you to show work for this right away, by the way, you can just write it down. We take 1 over 0.645 revolutions per second. And when we do that, we're going to end up with 1.55 seconds. So the first part of this, which is very important for everybody to understand, is that they're giving us the period. And so we need to deal with these equations for circular motion with the period in mind. And so let's just, before this gets out of hand, go ahead and write down the knowns. So the first one we're going to write is the period. That's 1.55 seconds. We were also given the mass, which was 0.750 kilograms. And we were also told the length of the string. Notice that's not the radius of the path, that's the length of the string. And so that's going to be given by the symbol L, which is 0.600 meters. And of course, we know G is 9.8 meters per second squared. And we're being asked here for the tension and the angle. And so, remember, I warned you. We've got a lot of work to do. Before we go ahead and do this work, though, I just want to go back and show one thing, like really quick. Being given the length of the string is actually not that bad. Because remember, we said the interior of the cone is a right triangle. So we have that, and we want this. That's not that bad. That's trig. And so we'll get to that in a minute, but I want you to keep in mind here that it's very important to remember that the interior of a cone is just a good old-fashioned right triangle. So I'm going to go ahead and draw a diagram down here, my free body diagram. This is going to be the same as it always was, and so I don't want to go like too nuts about this, but let's just show here that dotted line. We'll show our arrow showing the tension. We'll show a teeny little weight. And then I'm going to show here, actually, that this also is the length of the string. This is the radius of the circular path. And there's my angle, theta. And so my first move, like always, and I believe I said that before, like always, you got to just kind of start these things from scratch. The x component of the tension is providing the centripetal force. And the y component of the tension is supplying the weight. So let's just go ahead and deal with the y direction first because I hope it's pretty obvious that this part is not going to be so bad, especially after the last example we looked at. We're going to have ft cosine theta, remember the sine and the cosine switch here, and that's going to be equal to the weight. And so if we go ahead and solve this thing for the tension, we get a pretty simple standard, and notice by the usage of the word standard here, literally exactly the same, expression for the tension. It's basically going to be that every time. With the x direction equation, though, on the other hand, we have our work cut out for us. So the first thing we can do here is we can say, well, ftx is just going to be ft sine theta. And we have the centripetal force is equal to mv squared over r. That doesn't help us, though, because we don't have v. We have m, but we don't have r either. And we don't have the tension. And we don't have the angle. So, like I said, we've got business to deal with. And so the first thing we need to recognize down here is that the angle given in this problem is given with respect to the vertical. And so for that angle, the radius is the opposite side of the triangle and the length is the hypotenuse. And so since the sine of any angle, you don't have to write this part down, but since the sine of any angle is the opposite over the hypotenuse, that means the sine of the angle is going to be the opposite side, the radius, over the length. And so that means, and this part I do think you should write down, what that means is that r is going to be equal to L sine theta. So again, the sine is the opposite over the hypotenuse. That's the radius over the length. And if we just solve that for r by moving the L to the other side, we get r equals L sine theta. That's what we get from using that whole bit that I just said before about the interior of a cone being a right triangle or like a cross section, however you want to think about it. So we can go ahead and put that in for r because we know that r is equal to L sine theta. Now, what we also need to recognize is that the speed given to us needs to be transformed too, because the speed, if you remember, was not given. The period was given. And so we need to rewrite this equation by inserting the period. And if you remember from the video about orbits, speed can be given as circumference over period in the form of the equation v equals 2 pi r over t, circumference over the period. And so we're going to do that first, and I think you're going to realize why in a second. So we have ft sine theta is equal to m times v squared. So that's going to give me 2 pi r over t, and I got to square that whole thing, and then that's going to be over r. So moving on, I've got ft sine theta, and that's going to be equal to m, 2 squared is 4, pi squared is pi squared, r squared is r squared. And then in the bottom, I've got this r, that didn't go away, and then I've also got this t squared in the denominator. And so notice this r is going to cancel with one of those r's, and that means instead of having the r in the bottom like it originally was, it actually comes upstairs to the top. And so that's the reason why ultimately I wanted to plug in the speed first, because that equation becomes a little misleading, because you're going to notice some nice stuff is about to start to happen. So again, what I have here is ft sine theta equals 4 pi squared. I'm just rearranging this to put the constants in the front. 4 pi squared mr over t squared. And so now that I have that form of the equation, 4 pi squared mr over t squared, now I can make my substitution, r equals L sine theta. And so I have ft sine theta equals 4 pi squared m L sine theta over t squared. And lucky for us, notice the sine squareds are going to cancel. Phew. And so what we end up with, and this is a little sloppy, I apologize, but I don't have a big whiteboard at the front of the classroom like I usually do. What we end up with here is the tension is equal to 4 pi squared ml over t squared, which is a lot less disgusting than something that would have like a trig function squared in it. What I end up seeing a lot of kids do and then sort of back themselves into a corner is they sub in L sine theta here and then they move it up there to combine it and they end up getting a sine squared theta and it's just a mess. You do the speed first, you realize that the R is actually in the top and then it just cancels the sine theta that's already in the equation. And so what we end up with this, and this is actually not that complicated to deal with. Once we get the problem into this form, it's actually kind of business as usual in terms of solving this as we did before. We have a lot of options. Notice both of these equations have an m, and both of these equations have a tension. But if we solve them for m and we set the m's equal to each other, then we don't get rid of, like the only variable we get rid of is the mass, and we already have that. So that would be silly. And just for the sake of being lazy at this point, you should realize since we have both of these solved for ft, you might as well just go ahead and set the tensions equal to each other. So I'm going to go ahead and set those equations for the tensions equal to each other. And so I'm just going to go back for a second. I've got mg over cosine theta. Mg over cosine theta is equal to 4 pi squared ml over t squared. So mg over cosine theta is equal to, just to make sure we don't copy it down wrong, 4 pi squared ml over t squared. Notice once again, we get another nice cancellation. And so basically that just gives us g over cosine theta equals 4 pi squared L over t squared. Now, of course, we really want to make sure we are able to answer the question here. Like, what the heck are we doing? So let's go back to the question. Remember, the question is asking us for the tension, and it's asking us for the angle. And by eliminating the tension, now notice I have an equation which is g, which has g, which I know, 4, I know that, pi is a number I know, L, and we have the length of the rope, and we have the period also. And so we can use this equation to just go ahead and solve for the cosine of the angle. So if I move the cosine of the angle up, the t squared up and over, and the 4 pi squared L down, I end up with cosine theta equals gt squared over 4 pi squared L. And that's an equation I can solve for the angle. So I have the angle theta is equal to the inverse cosine of g t squared over 4 pi squared L. And so that gives me cosine -1, inverse cosine of 9.8 meters per second squared times the period, which I actually happen to remember is 1.55 seconds. And you got to make sure you square that. And then we have that over 4 pi squared L. And I think that was 0.6? 0.600 meters. And so we can plug that in, 0.600 meters. And that's our equation for the angle. You got to make sure you do 1.55 squared in your calculator, then you do times 9.8, then you divide it by that whole denominator, 4 pi squared times 0.600. And when you do that math, you end up getting a weird angle, but a perfectly fine angle nonetheless. It's 6.29 degrees. And that's our angle theta. And so notice, because the question here said to solve for the angle and the tension, now we're in business to solve for the tension. Make your life easy. You have a choice between two variables, what you want to go ahead and solve for, or you have a choice between two equations for the tension. Use the y equation. It's much simpler. It's less thing for mistakes. Nothing squared. It's easy. Ft equals mg over cosine theta. And so if we use the equation Ft equals mg over cosine theta, simply enough, it reduces to the mass 0.570 kilograms times 9.8 meters per second squared over the cosine of the angle here, which is 6.29 degrees. And when you do that math, you take that weight mg and divide it by the cosine of the angle, you get 7.39 newtons. And I feel like what I usually say at the end of these problems is, and that's it. But that was obviously quite a lot. However, the fact remains that is the conclusion of the video today. So I understand that that's a lot. And I understand that when I teach this in class every year, kids have issues with it. It's complicated. It takes like a couple days to really figure out and understand and get comfortable with. But I really want to stress and emphasize here, ask questions about this if you have them. This is not the easiest problem to understand, but it's an important problem because I always used to tell them, they could ask this as an experimental design, and then one year they did. And it was on a practice exam, not an actual exam. So it still is fair game for the actual exam. I wouldn't put it past them. So this is a problem you absolutely need to know how to do. And I've seen what you've done all year. There's no way that any group I've ever had in person is just actually smarter than you. But just ask questions. This is a tough one, but you will be able to figure this out if you put in the effort. So just make sure you review whatever needs to be reviewed about this one. You go back to basics and think about basic concepts. X tension's giving you the centripetal force, Y tension's giving you the weight, and then the rest of it really is just algebra. But I want to stress and emphasize, if any part of this video was confusing to you today, please, please, please ask whatever questions you may have about it. All right, everybody, enjoy the weekend.